Hi everyone, welcome back to the session. Let's wait for a couple of more minutes and then we will get started with our another session for understanding CCNA. All right, I'm sharing my screen and let's begin. My screen should be visible now and I guess we're good to start. Yeah. All right, so in the previous session, we spoke about the subnetting and we tried understanding how subnetting can be uh, done for different classes, class A, class B, class C. Tried out multiple questions, and I'm hoping that you all must have practiced it a little so that you guys can prepare yourselves better for submitting questions in your CCNA exam, right? I would also suggest you to keep on practicing these things because they are going to really help you not just in cracking your exam, but also in your production environments. Like when you will be a network engineer working in some organization, these things definitely help in getting better at your job. Keeping that in mind, let's continue and let's talk about something really important, which is understanding the networking models. Now, yesterday, when we were working on subnetting, or earlier when we were discussing, we mentioned sometimes the word layers, right? Layer 2, layer 3, and so on. So there is a networking model, which is basically based on 7 layers, which we use to understand networking from the very scratch to advanced concepts. When we talk about the networking model, these are kind of languages which are used by computers to interact with the other devices. So basically, a networking model is a stack of protocols and standards that works together to let my PC communicate with the other PCs. Earlier, when internet was very new and we didn't realize that, okay, that networks will grow this big. When it was the beginning of internet, every vendor used to have their own networking model. For example, if it was a IBM PC, IBM would have its own networking model. If it would have been a Apple PC, Apple would have its own networking model. Now, making IBM communicate with another IBM device was not a very difficult job. They both were using the same networking model, same standards, same protocol. So it was an easy job to connect both the IBM devices. But making IBM communicate to Apple was a really tough job because Apple devices were based on some different protocols and different standards, and IBM devices were using altogether different standards and different protocol. Then, the moment organization realize that networks are going to grow big, they realize the need of an open standard networking model. Basically, something that can work with IBM, something which can also work with Apple. Open standard networking model means which can be used with all the vendors. Okay. So now organizations and individuals started working on creating something that could be used as an open standard networking model. And we got two things out of it. We got two models out of it. One was OSI model and the other was TCP/IP. OSI stands for Open System Interconnection. And another one was TCP/IP, which stands for Transmission Control Protocol, and IP stands for Internet Protocol. So basically, they were used as the common base of the communication between two devices, which we can understand with a quick example. Assume that this is my first person, person A, who can only speak and understand English. Then there is another person, person B, who can only speak and understand Spanish. What do you think? If I want them to communicate with each other, would they be able to speak or exchange their ideas with each other? Yes or no? Do you think these two guys can communicate and share ideas with each other? No, right? If I both, if I make them both learn about a common language, let's say Hindi, would they be able to exchange their ideas? Yes, right. Similarly, when there were different vendors using different networking models, it was quite hard for them to exchange data with each other. But if I make them use a common networking model like OSI or TCP/IP, they would be easily able to communicate with each other because they are now based on same rules and same protocols, same standards, right? So let's understand how these networking models work. First, we'll speak about OSI model. OSI, which stands for Open System Interconnection, is made up of 7 layers. Does anyone know which organization created OSI model? ISO. Perfect. What does ISO stands for? Perfect. So OSI was created by an organization called ISO, which is the International Organization for Standardization. And this OSI model is made up of 7 layers. What are these 7 layers? Let's try to learn them. Application, presentation, session layer, transport layer, network layer, data link layer, and physical layer. Application, presentation, session, transport, network, data link, physical. Every layer has its responsibility and a job to perform, and they all work together to let us communicate from one device to the other or use the network services. For example, when you browse your internet, when you access your internet, you are actually using these 7 layers. Similarly, when you are sending some message or sending some email, you are utilizing these layers. Okay. So these 7 layers work together to help us achieve our tasks. What exactly happens? The data travels through all these layers, starting from the application layer, and moves in a top to down approach. So if basically I have a sender here, which is PCA, and then I have a receiver here, which is PCB. So what will happen? My data, which I'm trying to send, will move from the sender to the receiver, and the data will travel like this from the application layer to the physical layer. At every layer, some information is added according to the layer's responsibility. For example, the application layer is responsible for connecting us to applications. Presentation layer makes sure that the data is readable. Okay. So every layer has certain responsibility according to which they add some information to the data. This process of adding some information to the data is called encapsulation. Then finally, when it reaches the physical layer converts it into signals and transmits it over the cable. And then it reaches the destination, which is my PCB, let's say. When it reaches destination, here the data travels from down to top layer. And every layer removes the extra information which was added. What does that mean? That extra information which every layer was added related to their particular job or responsibility will now be removed at every particular layer. And then the final data would be represented or will be received by the user. This process of removing the extra information from the data is called de-encapsulation. Clear, guys? Perfect. Now the question is, what exactly are their responsibilities and what type of information do they add? So we'll start speaking about them one by one. We have the very first layer, as our application layer. So let's understand what application layer is responsible for. Memorizing the name of all the 7 layers is quite important. So make sure you learn them. 7th layer is yes, Ravi, I'm going to talk about the responsibility of every layer. What is the 7th layer of OSI? Application. Perfect. What's the 6th layer, guys? Presentation. 5th layer. That's session layer. Perfect. What's the next one? Transport. 3rd layer. Network. Then data link. And then what about the first layer? After data link, physical layer. Perfect. When we speak about our 7th layer, which is the application layer, it is responsible for providing network services to the applications. Okay. When you open your browser and you search for something, do you see in the URL box the protocol HTTP or HTTPS is something which is used? Have you ever observed that? In the URL box, you would be finding HTTP, HTTPS written in the beginning, right? So that is an application layer protocol that helps us in fetching out the web pages from the web servers and so on, right? So basically, HTTP or HTTPS is an application layer protocol, which is helping my browser to utilize the network services. Similarly, there are protocols like FTP, which are used for transferring files. And there are protocols for sending emails and so on, right? So application layer makes sure that it provides the network services to applications. So in the OSI layer, we can say application layer is the one closest to the user, and it provides the services to applications. And these services can include email, can include file transfers, can include web browsing, like we discussed. And yeah, so that's the responsibility of our application layer. The next layer that we have is the presentation layer, which ensures that the data is readable. Ensures that data is readable. So it makes sure that the data sent by application layer of one device is readable by other devices also. For example, when you receive a Word file, you need to make sure that it opens up with the extension as DOC, right? When you get an image, you need to make sure that it opens up with the extension of JPEG. So making sure that information that you have received or the data that you have processed is something which can be understood by the receiver is something which is the role of the presentation layer. Encrypting or decrypting the data to improve security, or processing the data, or translating the data in a form which is readable by the user is what presentation layer does. Any questions in that? Okay. Next layer we have is the session layer. Session layer is responsible for establishing we can say it establishes, manages, and terminates sessions. What does that mean? It is responsible for making sure that sessions are maintained parallelly when the communication is happening with more than one host. For example, when you open your browser, sometimes what we do, we open multiple tabs, right? Assume that uh, this is your PC, the client device, and there are multiple servers, right? This is the web server of YouTube. This is the web server of Google. This is the web server of Facebook, and then PyNet Labs. What I did, I opened my browser and I first of all, in the very first tab, I have opened pynetlabs.com. So I will say a session will get established between my client device, which is my PC, and the web server of PyNet Labs, right? Then in the next tab, I created YouTube. I opened google.com and Facebook as well. So some sessions will also be created with these particular websites. My question to you is, have you ever experienced that when probably uh, you are maybe watching something on YouTube, yeah, that video suddenly starts playing in the, let's say, in the Facebook's website? Is it possible? Or do you see sometimes that on your YouTube's website you start receiving Facebook's post or images or content? No, right? How does that happen? That happens because of the session layer. Why? We are ensuring that there is one session which is maintained between the client and the YouTube site, then another session maintained between client and the Google. So we don't want the data to get mixed up, right? Similarly, when we close these websites, let's say I closed the tab of youtube.com. So terminating that session is also a responsibility of my session layer. So creating, managing, and terminating sessions is what session layer is responsible for. And it makes sure that the two communicating devices can exchange their data, and the data does not also gets mixed up with the other sessions which might be going on with other websites. Then sometimes when you use internet banking, on the internet banking, if you leave your PC idle for some time, it gives you a pop-up saying connection timed out, try again. Have you guys experienced something like this? Right? So that is also, we can say, termination of a session when there is no exchange of data. As I leave my PC idle for some times to make sure that the data is secure, my session automatically gets terminated. Clear, guys? That's what we have session layer for. Next, we have the transport layer. Transport layer ensures end-to-end connectivity between devices. So transport layer has got many responsibilities. And there are two main protocols that work on this particular layer to fulfill these responsibilities. Can you guys name them? TCP and UDP. So let's understand first of all, what are these protocols? There are two transport layer protocols, TCP and UDP. TCP stands for Transmission Control Protocol. And UDP stands for User Datagram Protocol. Clear? When we talk about TCP, we consider TCP as reliable. I'll explain all this, don't worry. We call TCP as reliable and we call UDP as non-reliable. We consider TCP as reliable because it provides acknowledgement. In the case of UDP, there is no acknowledgement. TCP does retransmission. In the case of UDP, there is no retransmission. TCP comparing to UDP is slow and this is comparatively faster. TCP is considered as connection oriented. UDP is connectionless. Then TCP has the protocol number as 6. The protocol number for UDP is 17. Okay. We'll try to understand all these things one by one. TCP is reliable and UDP is non-reliable. Why do we say so? Because TCP does provides an acknowledgement of the data that you are sending. In the case of UDP, there is no acknowledgement. So for example, I'll tell you about this through an example of courier service. Okay. Assume that you have two branches. There is branch A and then there is branch B. You want to send some files from your branch A to branch B. And there are two courier services, TCP and UDP. So I have sent, let's say, some files through the TCP courier service. What it is going to do is it will take the files to the branch B, will deliver those files there, and will come back to me, giving me an acknowledgement or a receipt. Yeah, it will tell me that, hey, I have successfully dropped your packets on branch B. That's the TCP courier service. Next time when I wanted to send some files, I have given it to the UDP courier service. So UDP services will also go to my branch B, will deliver the packet, but will not consider coming back to tell me that the packets were delivered successfully. It will continue ahead, will go to the next project and will basically continue working. This is basically providing acknowledgement in TCP, but there is no acknowledgement in UDP. Clear? Protocol number, Saurabh, is the identity which we use for different protocols. So TCP has the protocol number 6 and UDP has the protocol number 17. Any questions so far? Okay. Then next time what happened? You again wanted to send some files from branch A to branch B. Okay. And there was some construction going on the road, and there was a pothole. So you gave the files to TCP truck. TCP truck was going, and because of this pothole, I somehow lost my packets. My truck got damaged, and all the files got destructed, and I couldn't deliver it to my branch B. Okay. So what TCP truck will do? TCP truck will come back to me, will ask me, hey, can you give me the files again? I have lost those files somehow, and I would like to deliver them on branch B again. This process of going back when the data is lost in the journey is called what? Retransmission. So TCP does that, but UDP, if it's moving and it has lost the file because of any XYZ reason, it will not come back. It will not ask for the files again to deliver them to the destination. But in TCP, like I said, it will come back, it will ask for the files again, then it will deliver it to the branch B, and then will be coming back for the acknowledgement also. So that's why we call TCP reliable, because it does retransmission, it provides us the acknowledgement, whereas UDP, it's non-reliable and provides us no acknowledgement, there is no retransmission. Are we clear so far? Okay. Then we have discussed why it is reliable, acknowledgement, and retransmission. It is slow, obviously, because it has got many responsibilities. Comparing it to UDP, UDP is faster because it has lesser responsibility. TCP is connection oriented, UDP is connectionless. Let's understand why. When TCP sends some file from PC A to PC B, it doesn't handshake. It handshakes with the destination device, where it checks with the destination device if they are received, if they are ready to receive some traffic. For example, if PCA wants to send some traffic to PCB, the very first message that my PCA is going to send is called synchronization message or SYN message. This is kind of a message which tells the PCB that, hey, I'm going to send you some data. Are you ready to receive it? My PCB says, yes, I acknowledge your request. I'm happy to receive that data. I would also like to send you some data. Would you like to receive it? My PCA is going to acknowledge that. And this process is called TCP three-way handshake. But in UDP, there is no such handshakes. UDP will directly start sending data to the other side device. Clear, guys? So in UDP, there will not be any handshake. That's why we call it connectionless, and we call TCP connection oriented. Okay, we do have a question here, very nice question. That where do we use UDP? If TCP is so nice, it does acknowledgement, it does retransmission, it is reliable. So why don't we simply use TCP? What is the use of UDP? Any guesses? Perfect. So like right now, we are connected on a Teams call, correct? Assume that my internet goes bad and packet starts getting dropped, okay? So when my connection will get established again, would you like the packets which I was trying to send earlier to receive now? Like, for example, right now we are talking about transport layer, and I continue the explanation. I speak about, let's say, next about the network layer and data link layer. But because of bad internet, those packets were not delivered to you. Now, later on, when connection gets established again, I start explaining data link layer. Okay. So while the explanation of physical layer or data link layer, would you like to receive the packets in between for the network layer? No, right? Otherwise, it will make no sense. If let's say I'm explaining physical layer and in between you are receiving my voice about, let's say, explanation of network layer, then it doesn't make sense. Right now, we have a league going on for cricket, IPL, right? Assume that there is a cricket match going on and you are watching the game, you are watching the batsman playing at fifth over, and suddenly your internet goes bad and the packet starts getting dropped. Now you see the loading sign for some time, you see it buffering for some time, and connection gets re-established at, let's say, eighth over. Now the batsman is playing at the eighth over. So would you like to receive the video clips or the shots that batsman played between the fifth to eighth over, or would you like to continue the live streaming from the eighth over? What do you think? You would like to continue, right? You would like to watch the live streaming. So not everywhere retransmission is a good idea. That's why UDP also is very important for all the live interactions, be it a video call, be it a voice call, be it live streaming. Such communication doesn't require retransmission. If there will be retransmission and that type of communication, it will create a mess. So that's why we go for UDP in such communications. But when we are, let's say, sharing some files, we can go for TCP, as that will help me in making sure that the files were delivered to the destination, right? That's how TCP and UDP differ from each other. Another job of transport layer is segmenting the data. I'll write it here. TCP is not just responsible for sending the data from one side to the other. It also does the job of breaking down the data into segments. How does that work? Let me write it here. Segmenting and sequencing is also what we find with TCP. For example, if you have a long message, which is, let's say, hi, welcome to CCNA training. So segmenting would be the process of breaking down the data into smaller chunks. For example, the first segment can have hi, second segment can have welcome, then third to CCNA, and then fourth to training. By breaking down the data into smaller chunks, it becomes easier for us to transmit traffic from one user to the other user. So now when I will send some traffic from PC A to PC B, it will move in the form of these segments. But it is also possible that my user B might receive training as the first segment, then to CCNA as second, then welcome as third, and hi as the last one. So will this message make any sense to the user? No, right? So what it does, it also does sequencing. It puts a number, an ID on every packet or every segment. So hi will be my first, second will be my welcome, third is going to be to CCNA, and fourth segment is going to be training. So that if the user receives it in some different order, like this, so it can rearrange the data and can put it in correct format to make the message correct, which is hi, welcome to CCNA training. That's called segmenting and sequencing the data. Any questions or doubts so far? Perfect. Then the next layer is network layer. Network layer has the responsibility of routing packets uh, towards destination using the best path. So you can say routing packets towards best path. And it does provides us the information about source IP and the destination IP. Okay. Let's understand the responsibility of network layer again with a example. Let's say you are in Delhi and you want to travel to Mumbai. Okay. Now to travel to Mumbai, you have three available options. One is through the highway one is through the highway number 2, and one is through the highway number 3. So do you guys use Google Maps? Yeah. What it does, it looks through all the available options. Then it calculates which particular path will help you reach the destination in the least time, correct? And then highlights it as the best path. That is what network layer does. It will check how many paths we have to reach the destination. Out of all the available paths, which one will help me reach the destination with the lowest cost or metric, which can be about making you reach the destination at earliest, right? And we'll consider it as best one. For example, let's say we decided we'll go from the highway 2. So we will consider highway 2 as our best path. Similarly, in the case of networking, what happens? When you are browsing your network or internet, let's say this is your home router, this is your PC connected, your home router, and this is the Google web server. Okay. So when you access google.com, there will be thousands or millions of paths through which you can reach google.com. But out of them, whatever would be the best path, we will select that to make you reach the destination, which is Google server. So that is what network layer does. It will find out what is the best path and will route packets on that particular path to make you reach the destination. Are we clear so far? Perfect. Now comes the responsibility of data link layer. Data link layer is responsible for hop to hop communication. We said that we want to move from Delhi to Mumbai. But in order to move from Delhi to Mumbai, the very first thing I'll have to do is I'll have to get from my room, get up from my room and get out of my house, right? After that, from my house, I will go to the nearest railway station. Let's say I'm going via railway. So I'll go to the nearest railway station, correct? That's going to be my second hop. First hop is basically from room to the main gate, correct? Then from main gate to, let's say, the railway station, that's going to be my second hop. From that railway station, I might catch a train which goes first to another, uh, let's say, state. Let's say it goes via uh, Haryana. So from Delhi to Haryana, that's again another stop. Similarly, it adds up, let's say, 5 more stops, and then finally it reaches the destination Mumbai's railway station. After reaching there, again from Mumbai railway station, I'll have to travel to my hotel, and that's again the final stop. So this stop to stop communication is something which is supported by the data link layer. It defines how the data should be transmitted from one device to the another device using the layer 2 addresses, which is basically the MAC addresses. Let's understand it again with the example. We said this is your PC and this PC is connected to home router. From home router, there is a connection which is going towards the ISP router, correct? Then that ISP router is connected to multiple other routers that can make me reach google.com. And there can be multiple connections with that router, right? I can have any sort of reachability. So first, I'll move out from my room and I'll go to my main gateway, the house gate, right? This is the router. Home router is basically my gateway to move out from my own network to a different network. Okay. So just like to go out of your house, what do you cross? You cross the main gate, right? Then you get out of the house. Just like that, the router that you are directly connected with is your default gateway or gateway to go out of your network. So when I wish to reach Google, the very first hop for me is my home router. That's going to be a communication first between my PC and the home router. So my first hop is home router. From home router, I'll send it to ISP router. That's my next hop. And let's assume that layer 3 decided that this is going to be the best path. Okay. So now from ISP router, the data would be sent to this router. It will be my next hop, then here, and then finally to the Google server. This hop-to-hop communication is supported by layer 2 address called MAC address. Are we clear about this? So we can say the data link layer is responsible for adding information about source MAC address and destination MAC address. Another thing to remember here, like I said, it's hop to hop. So what will happen? First, my source MAC will be the MAC address of my PC, and destination MAC is going to be the MAC address of my home router. Make sense? Once the packet reaches home router, now from home router, I have to give it to ISP. So source MAC will become the home router's MAC address, and destination MAC will become the ISP's MAC address. Similarly, when it reaches ISP, now it has to be moved to this router. So source MAC will become ISP's MAC and destination MAC will become this router's MAC. When the packet reaches here, it will again change the source MAC and destination MAC to send the traffic from this router to this router, again from here to here, then again from here to here. Make sense? But throughout this communication, IP addresses will remain same. The source IP is going to be this and destination IP is going to be this. This will make more sense later on when we'll look at some practicals and we'll understand the packet analysis. But as of now, just understand that hop-to-hop communication is supported by layer 2 and the best route is found out by the layer 3. Questions or doubts in this so far? So we have a very nice question here. How will we get next hop router's MAC address? Like how do I know the MAC address of home router? Or how home router will know the MAC address of ISP? There is a protocol used for that called ARP. We'll discuss about it later on. So I'll talk about it, don't worry. Any other questions? Vijay, try to attend the sessions live and recordings will be made available, but not right now, later on in the month. Yeah. how to know which path is nearest for reaching google.com. So Abhishek, there are different routing protocols, and these routing protocols use different metrics to find out which is the best path. Some routing protocol will use bandwidth, some will use delay. So there are formulas for finding out the cost of all the possible paths, and then whatever path will have lowest cost will be considered as the best path, which we will take for reaching the destination. So it depends on the routing protocol. Okay. Lastly, we have physical layer. Physical layer defines all the physical aspects of the network, like the different connectors, different cables and stuff. Along with that, it does the translation of data into bits and transmits, we can say transmits it on media. So if you are connected through cable, it will transmit it on cable. If you are connected through wireless networks, then it will transmit it through the radio frequencies. It does the conversion into bits and then uh, basically transmits the data. Yes, Bhanu will be speaking about routing protocols later on. Any other questions? All right. So guys, OSI, I'm going to give you a little shock here that OSI is not what we use on devices. OSI is just a reference model which we use for studying the networks. Actually, on my PC and on your PC, on the routers or the network devices, we are using TCP/IP, which is the other networking model. TCP/IP, that stands for Transmission Control Protocol, and IP, which stands for Internet Protocol, was created by some individuals of DoD US Army with the help of industry professors. So DoD stands for Department of Defense. From the Department of Defense of US Army, some individuals with the help of professors of universities, they created TCP/IP, which is the networking model we use on our devices. Okay. Now I am giving you a short break of 10 minutes, but I have a question for you, which you have to try getting an answer for. The question is that OSI model is so nice, right? It tells you everything in so detail. It gives you a good understanding of network. Comparing it to TCP/IP, TCP/IP has a lesser number of layers. It is based on OSI, like TCP/IP. Uh, some protocols of TCP/IP do take reference from OSI model only. Then whenever we study networking, we study it through OSI model. So my question for you all, which you have to try getting an answer for in these 10 minutes, is that if OSI model is so nice, it explains networking so well, if it is something which even TCP/IP take reference from, then why are we simply not using OSI? Why do we have TCP/IP on our devices? So try to find an answer for that, and then we'll connect back again in 10 minutes. We'll learn about TCP/IP and we'll discuss why we use TCP/IP and not OSI. Let's be back in 10 and then continue. All right, everyone must be back from the break. So let's understand what is TCP/IP model and how it is different from OSI. And then I'll read your messages and your responses. I can see some of you have already mentioned the reason why we are using TCP/IP and not OSI. So good job, everyone. You are very correct here. Let's understand what is TCP/IP so that we can know the differences between them. As we compare OSI model to TCP/IP, OSI has got 7 layers. We'll quickly revise the 7 layers again by naming them one by one. So OSI model has how many layers? 7 layers. And we have got the 7th layer as application layer, 6th layer as presentation layer, 5th layer as session layer, 4th as transport, 3rd is the network layer, 2nd is the data link layer, and the first one is the physical layer. These are the 7 layers of OSI model. When we compare it to TCP/IP, TCP/IP has just got 5 layers in its stack. The very first one is the application layer. Next, we have transport layer. Then we have internet layer. Then we have data link layer. And we have physical layer. These 3 layers, application, presentation, session layer, they get combined into one in the case of TCP/IP, which is called as application layer. The responsibility are still going to be addressed by this particular application layer. So we'll still perform the responsibility of presenting the data in appropriate manner. We'll still perform the responsibility of making sure that sessions are created, sessions are terminated. But now we just have a single name for all of them, or we can say they are getting combined into one called application layer. Transport layer stays the same. It is still there in TCP/IP with the same name. Network layer is there, having the same responsibilities, same tasks, but with a different name called internet layer. Data link layer is still there, physical layer is still there. As per some documentations, these two layers are combined together into one network access. Okay, that is also correct. That's also not wrong. So some documents say that TCP/IP is a 4-layer model, whereas some say that TCP/IP is a 5-layer model. Both are correct. Sometimes you might find data link and physical layer just written as one called network access, right? And sometimes you will find both the layers written individually as data link layer and the physical layer. Both are correct, both are right. Make sense? Perfect. Then we use some terminology for representing data on these different layers. As per the OSI model, if data is at application layer, we'll call it L7 PDU. PDU stands for protocol data unit. Just like we have centimeter, meter for measuring distance. Just like that, protocol data unit is something that we use for measuring, we can say, data of different protocols. So if the data is operating at layer 7, we call it L7 PDU. When it reaches layer 6, we term it as L6 PDU. And as you can guess, it will be L5 PDU here, L4 PDU here L3 PDU, here L2 PDU, and L1 PDU. On the other hand, when we speak about TCP/IP, TCP/IP calls data as data at the application layer. At transport layer, we term it as segment, as we break it down into smaller chunks, right? At the internet layer, we call it as packet. At the data link layer, we call it as frame. And on the physical layer, it gets translated into zeros and ones, so bits. Yeah. Then I'll also show you how the headers are added. Assume that this is your data. This is your data, okay? So when data reaches the application layer is going to add some information on top of it, which will be called as header. So when we attach something before data, we call it header. This is going to be my layer 7 header. So I'll just write it in short form as L7H. This will contain information about the application that we are using. Then the data moves to the next layer. Next is my presentation layer. So to make sure that the data is readable, my layer 6 also will add some additional information to it, will encapsulate some data to it, which is going to be my layer 6 header. Then again, when it reaches layer 5 will be responsible for defining the information related to different sessions. So that information is encapsulated by layer 5 with the help of a layer 5 header. I'll write it here. Layer 5 header is going to be added. Then afterwards, it reaches the transport layer where we decide whether the transportation protocol should be TCP or UDP. And we perform the task of segmentation and sequencing. So layer 4 also adds this additional information in the form of a header, which we call as layer 4 header. And now this basically will be termed as segment as per the TCP IP. Okay. Then it reaches layer 3. What does layer 3 adds, guys, to the packet? No, Saurabh, headers are headers only for all the layers. It's the complete thing which we call as data on application, presentation, and session layer. Then this complete thing here on layer 3 will be, sorry, layer 4 will be termed as segment. Then when layer 3 header is added, which is going to contain source IP and destination IP. What do we call it, guys? We call it packet, right? Then my data link layer adds its own header. So the same thing will move to the data link layer, where the header will be added. about source MAC and destination MAC. And along with that, it also adds something at the end as well called trailer. So data link layer is going to put a header, which we will call as layer 2 header, but along with that, it adds something called as trailer as well to the packet. And now this is called as frame. What is the use of this trailer? Let's understand. This is used for ensuring that uh, data is correct and is basically used to detect errors or the data dignity while the transmission of data from one side to the other. An example of checking that whether data is received correctly or not is through a method of sequencing, which is FCS. An example of sequence is frame check sequence. FCS applies a formula to the data and calculates a value out of it. Okay. Then the same calculation is done by the receiver to make sure if the data was received as original or if there are some errors. So for example, when PCA is sending some information to PCB, PCA will apply a formula to that information and will calculate the frame check sequence. Now PCB will receive that data, will apply the same formula and will calculate the FCS value. If the FCS value comes out to be same as the PCA mentioned, then we accept it. If it comes out to be something different, we understand that there are errors in the received data. So we deny that packet and we ask for it again, depending upon TCP or UDP protocol. So we can say the receiver is going to use this information to detect the error and to figure out if the information received is correct or not. After the layer 2, the data gets translated into binaries and is transmitted over the connected medium. What questions or doubts do we have in this? Okay, give me a thumbs up if whatever we discussed about OSI and TCP/IP is clear to you. FCS value is stored at the end of your packet. When it reaches data link layer, at the end, a trailer is added in which this value is stored. This is done by the source first. Then it reaches the destination. Destination also calculates the FCS. If it comes out to be same, we accept it. If it is found to be different, we understand that the data was manipulated over the path and we deny it, assuming that the data is not correct. Physical layer has the responsibility of translating it into bits. So no header or no information we can say is added. The rest, you can say the physical layer will do the job of translating the bits and converting it into signals so that it can be transmitted over the cables or radio frequencies. What other questions do we have, guys? Okay, perfect. So we'll look at the working of ARP protocol, and I'll also tell you about an amazing simulator, Cisco Packet Tracer, which we'll be using for performing our labs. But before we jump onto that, I quickly want you guys to understand a couple of details related to MAC address and IP address. a quick introduction basically so that we can proceed ahead with the discussions. No, Saurabh, like I mentioned earlier, layer 1 is just responsible for translating it into bits. Okay, what is the full form of MAC address? MAC address stands for Media Access Control. And IP address stands for Internet Protocol address. A MAC address looks something like this: 1, 2, 3, 4. Let's say A, B, C, D, 0, 0, 1, 1. That's a MAC address. Whereas an IP address looks something like this: 192.168.1.1. The form of the MAC address in which it is written is called as hexadecimal, where decimal starting from 0 to 9 are included, and the alphabets starting from A to F are included. On the other hand, IP address form is called as dotted decimal form. Then MAC address is the unique address. It is added on a card called NIC, which I have told you about earlier. Can someone quickly let me know what is the full form of NIC? Network interface card. Perfect. So it is burned on the network interface card. That's why we also call it burned in address or hardware address. Okay. Whereas IP address is something which can be unique, can be same also when it is a private network. So we'll not talk about it like right now. It depends on the situation we are in. But yeah, MAC address is called the hardware address, and IP address is called the logical address. The size of a MAC address is 48 bits. The size of an IP address is, we have discussed this in the previous session. Let me know quickly. 32 bits. Perfect. 32 bits, right? So when we initiate some communication from, let's say, PC A to PC B, when I initiate or send some traffic from PC A to PC B, what do? I specify my destination using the IP address of my PCB. So assume that the IP on my PCA is 210.1.1 and IP on my PCB is 210.1.2. So first of all, let me know, can they communicate with each other without the need of router? Yes, because they are part of same network, right? Assume that the MAC address of PCA is AA AA and the MAC address of PCB is BB. Okay, we are taking it as an assumption. These are not the valid formats or the accurate MAC addresses. So PCA has the IP 210.1.1, PCB has the IP 210.1.2. So when I will send some traffic, a packet will be generated in which there is going to be source IP, there is going to be destination IP. There's going to be source MAC, which is added by layer 2, and destination MAC. Source IP, my PCA will know, obviously, it will know its own IP address. So it's going to add the source IP. Can you let me know what will be the source IP if communication is happening between PCA to PCB? Two hundred ten 1.1. What will be the destination IP? 210.1.2. Source IP, PCA will know by its own, like that's the IP of myself. So I'll know what's my IP address, right? Destination IP is added by the user. Source MAC also is a personal information for PCA. So it will know its own MAC address and will add the MAC address as AA. But what about destination MAC address? When we initiate some communication, when we send some ping or when we use some service, do we specify the MAC address of destination? Have you ever done that? No, right? So destination MAC address is something that we are not sure about. And we learn about destination MAC address using a protocol called ARP. ARP stands for Address Resolution Protocol. Clear? Address resolution protocol helps me in learning the destination MAC address. So what will happen when I will initiate some communication from PC A to PC B? First, I'll have to figure out what's the MAC address of PC B. To learn about the destination MAC address, I will use ARP protocol. ARP is going to generate a message called ARP request. And ARP request is broadcasted. That means it will be sent to everyone, whoever is connected to me. Inside the ARP request message, we add a question basically. In simple language, it's a question that who is 210.1.1. Clear? Now, because everyone is going to receive it, so I can say my PCB will also receive it, right? So PCB will receive this message. What it will do, first of all, PCB is going to store MAC address of PCA in its database. And then will generate an ARP reply. Step 3 would be sending an ARP reply to PCA specifying that I am 210.1.2. Okay, this question was about 1.2, sorry. 1.1 is myself only. So I am 210.1.2 and my MAC is BB. Now step 4 will be that PCA stores this MAC in ARP cache. ARP cache is nothing but the database I was talking about earlier. So it creates a cache where it will put the MAC address of my PCB and will forward traffic. So someone had the question earlier that how is destination MAC learned? So this is the procedure, guys. That's how the destination MAC addresses are learned from the devices. Any questions or doubt in this? Okay, I'm going to share my another screen, which is of Cisco Packet Tracer. I will teach you guys how you can get this packet tracer installed on your local devices. But first, I just want you to understand what we have learned. I'm hoping my screen of Cisco Packet Tracer is visible now. So this is just a Cisco's provided simulator where you can create your labs. You can test different protocols, different configurations. We are going to use this simulator only for understanding and learning CCNA topics. As of now, I'll give you a quick introduction and we'll try to show you how ARP works here. Yeah. This is Cisco Packet Tracer. There are some options available here on the top side. These can be used for creating files, folder, and saving them, printing them, zooming in, zooming out, all the basic stuff. This is used for making selections. This white area is your logical workspace. You can design your topology here. You can add devices and create your network. We have the option of inspecting devices, deleting devices, resizing, adding a note, uh, creating shapes, all of that, right? Adding some messages and stuff. Then if you select any other mode, let's say I selected the delete mode. So right now, whatever I will click, that will get deleted. So to get back into the normal mode, I can select back onto the very first option here, which is select mode, the normal mode. Okay. I'll give you a good introduction to it in detail, but as of now, let's talk about ARP quickly. Otherwise, we'll get distracted and we'll forget about it, right? So I'll take two PCs. That's how you select a PC and you add it in your topology. I have added PC 0 and PC 1. Then I will go to this section called connections and I'll connect a cable from PC 0 to PC 1. And like we discussed, I'll put the IP 210.1.1 on PC 0 and 210.1.2 on PC 1. So let's do that and we'll try to observe ARP after it. PC 0 desktop IP. Guys, don't worry about how to use this particular Cisco packet tracer. I'll teach you. As of now, I'm just showcasing how ARP works. Then I'll show you how you can get packet tracer and use it. Okay. I've added IP addresses. Now I'll select the simulation mode where I can see the packets moving. And I will create a ping message, or you can say I'll just send some traffic to the destination 210.1.2. Okay. Ping is the protocol, or you can say a tool under the protocol ICMP, Internet Control Message Protocol, which we use for checking connectivity. If you would have some idea of IT industry, you will already know what is ping. And those who don't know, it's just used for checking reachability between devices. Okay. So right now I have initiated a ping message. And if you see here on the right side, we have one ICMP packet, which is the ping packet, and then we have ARP packet. If I click on the ARP packet, we can see here some information. We can see that there is a source MAC, which is 0000CB41050. That's the source MAC, which is basically the MAC address of PC 0. Okay. And then the destination MAC is fff.fff.fff. This is the MAC address when we are broadcasting something. So when you broadcast a frame, the MAC address used for that is all F. Clear, guys? Give me a thumbs up if that's clear. Okay. Source IP is 210.1.1. Destination IP is 210.1.2 because I initiated it from PC 0 to PC 1. Okay. If I say next, you can see this green packet, which was of ARP, moved from PC 0 to PC 1. Now PC 1 will create an ARP reply, which will be sent back to PC 0. Okay. After I have got the destination MAC at PC 0, my ICMP packet will come forward, which was the ping packet. and then that communication will start happening. Now, if I click on the next button, my ICMP packet goes to the destination and then comes back with the reply of ICMP. Clear, guys? So anytime you are initiating some communication and you are not sure what is your destination MAC, your packet will be put on hold. You put your packet in the parking lot and you say, let me figure out the destination MAC first using the ARP protocol. ARP will send out ARP request and will receive an ARP reply. Okay. Once we have got the ARP reply, once we have got the destination MAC address, after that, you will bring out the packet from the parking lot and you can send that packet to make it reach the destination. Questions? Okay. Now I'll switch back to the real time mode and the communication will happen. And yeah, that's how the ARP works. Let me know if you have got any doubts or queries on this. Cisco Packet Tracer, how to download it, how to get it, I'll teach you, don't worry. What does ping stands for? Ping doesn't stands for anything. It is a part of ICMP protocol. It's a utility, so it's not a short form. It's a utility, a tool which is used for checking reachability. How it gets all broadcast MAC when we send from PCA, which has its own MAC address. Source MAC, Rahim, is the PCA's MAC address, but destination MAC is the broadcast MAC address, which is all F. So because we want that packet to be broadcasted so that out of all the connected devices, whosoever is 210.1.2 can reply me back. That's why we broadcast it, because we don't know, right, who is 210.1.2. We don't have the MAC address of that PC. If we had the MAC address of that PC, then we would have directly sent the packet to that particular PC. Why to broadcast it? Correct? Like for example, right now, my PC0 has learned about MAC address of PC1. And we can also check that in my command prompt by writing a command arp-a. So arp-a tells us about the arp cache. Okay. So it tells me that there is a IP address 210.1.2 whose MAC address is this 0090, this one. Yeah. So now if I again, let's say, send some traffic from PC0 to PC1, this time I don't need ARP. Why? Because I already know the MAC address. So I'll directly send the packet from PC0 to PC1. See, no ARP is required. Okay, we have another question. If IP is available, why do we need MAC address? What is the use of MAC address? Sham Sundar, think about the example that I was talking about earlier, where you are communicating from your PC to the Google server. Now, you know the IP of your PC, you know the IP of Google server, for example. Okay. So you have initiated a request of reaching Google server. But to reach that Google server, there will be multiple hops that will help you to reach the destination. Correct? So to make that hop to hop communication, MAC addresses are required. In this case, we just have two devices, but a network can be as big as internet also, right? So to learn the hop to hop communication, we need MAC addresses. Is ping and traceroute same? No, they are not same. Ping basically helps you check the reachability. Traceroute tells you about the path your packet has taken. So once we look at some more topologies and examples later on, I'll tell you how traceroute works. Sanju, you can remind me about this question later on when we will be doing some bigger topology with a different example. So that will explain us traceroute in a better manner. Yeah. Okay, now it's time to learn how to get this amazing simulator packet tracer on the local machines. Very simple. You can get it for free from Cisco. I'll open my browser here. And on my browser, you just have, like on your internet browser, you just have to type down skill for all. Okay, just a second. Yeah. So here I'll search for skill for all. And similarly, one more tab I can open here, Cisco Packet Tracer PyNet Labs. So we have a blog about understanding what is Packet Tracer and its feature. You can read this blog, what is Cisco Packet Tracer, why to use it, and how to download it. It is mentioned step by step. You can download the Packet Tracer tool from Skill for All page. So yeah, you guys can follow this blog as well. And rest I'm telling you how you can download Cisco Packet Tracer. You guys can make a search for skill for all, and I guess they have skills for all Cisco. Yeah, I believe they have switched back to netacad.com. So let's see. Yep. So on netacad.com, which is from Cisco, you can enroll to various programs. And Cisco Packet Tracer is also something that you can get from this website. The very first thing that you need to do is you need to log into your Cisco account. So if you do have a Cisco account, you can directly log in. Otherwise, you have the option of signing up. You can sign up, you can specify your country, state, and other details. Continue to add your email, continue to create a password for yourself, and so on to sign up for yourself, right? I do have an account already, so I'm going to log into that directly. Once you sign in the search box, you can type down Cisco Packet Tracer. You will see this course named as Getting Started with Cisco Packet Tracer. Okay. I see the button as a resume course. You will see it as enroll to the course. So you can just click on enroll and you will get enrolled to the course. It is available for free. Once you have got enrolled to the course, you can scroll down and the module number 1 tells you how to download and use Packet Tracer. Expand it. It tells you install Cisco Packet Tracer. And the chapter 3 is about downloading Cisco Packet Tracer, right? So I'm gonna just avoid all of that and click on resources. Yeah. Okay. Again, what you can do is enroll yourself, click on resources. You will see Cisco Packet Tracer options here. But no, we don't need to get there also. I'll begin with the first chapter. So resume course. And my chapter number 3 is about downloading Cisco Packet Tracer, where I have this link from where I can get Cisco Packet Tracer. So I'll click on it. I'll open it in a new tab. I'm also pasting this link in the Telegram group for you all. But yeah, like I said, you will need an account to get to this particular page. Here you can scroll down and can get Packet Tracer as per your operating system. If you have Windows, you can go for this option. If you have Mac, then this option. If you are using Ubuntu, then this option. Clear, guys? Once you get Cisco Packet Tracer installed, you can open it and it will give you a page looking like this. Here on this page, there are various options to explore. If you will try to use it by yourself, you will get a good amount of idea about the tool. But a quick introduction here from my side also. Like I said, these are some tools which can be used for creating a new file, opening a new file, saving the file, printing it, and so on. Then on the lower banner, we have select option, we have inspect option. Inspect can tell you about the details. See the port status summary. If I click on that, I can see what's the port status and stuff. I can see those details there. Then the next tool is about delete. If I click on that and click on the device, it will ask me, do you want to delete? Yes, delete. If I click on the note, it deletes that. So wherever I click, it will delete that item. So now to get back from the delete mode to the normal select mode, I can click on the first option again, like this. Okay. This is for resizing. This is for adding notes. Like you saw, I was writing the IP address as the note. So if you want to type something in your topology, you can type it down using these notes, which can be an IP address, can be your PC name, like this, and so on. Then you can add lines, you can add rectangles, circles, and any shape you want. This is for creating a message from one side to the other side. Like if you might have observed earlier when we had the two PCs, this option lets you send a packet from one PC to the other PC. Then this is again something to add complex PDU. Like if you want to make some modifications and do customization, you can do that. These are how these options work. Then on the bottom side, there are different categories of devices. The very first category is network devices, if you see. Under that category, we have routers, we have switches, we have hubs, wireless devices, security devices. Under routers also, we have multiple options. If you see, there are different series of routers, like the normal routers, the basic routers, then the ISR routers, the big routers, and so on. So different router platforms can be explored from here. Similarly, if I click on switches, switches has got certain different we can say types of switches which can be used as per our requirement. Like I said, gradually when we will work with the labs, we'll create some scenarios for our practices. We'll get a better idea of packet tracer and these things, obviously, right? Then hubs are of no use for us. We don't have a use of wireless devices as of now. Then we have got security devices. We have got some WAN emulations. Then we have the category end devices, endpoints, basically PC, laptop, server, IP phone, IPTV, and so on. Whatever end devices are there, you can use them. You can add them from here. For example, like I added PC, if I want to add a laptop, I just need to click on it and I can put it wherever I want. Let's say here. Yeah. Then similarly, let's say I want to add 5 more laptops. So what I can do is I can press my control button on the keyboard and can click on the laptop option. This will allow me to add multiple devices at the given point of time. Now, wherever I click, a laptop is going to get added. If I press escape button, or if I click on the select option again, I'm back into the normal mode. Now, if I click anywhere, it doesn't add the laptop. Okay. Again, I'll repeat what I have explained. First of all, I'll select all of them. Then I'll click on delete option. I'll delete all of them. This one also. Yeah. Then I'll click back on the select option to get back into the normal mode. Now I want to add, let's say 5 laptops. So if I click on it once and I click on my screen once, we can see a laptop is added. But then if I want to add more, I'll have to select it again. Instead of that, I can select the laptop while pressing the control key of my keyboard. This will allow me to place multiple routers all together in one go. Make sense? Is that clear? Give me a thumbs up. Awesome. So that's a way of adding multiple devices. Then we have another category, components. Again, not something of our use. We have a category called connections. Under connections, you can find different types of cables. You can find crossover cable, copper cable, straight through cable, fiber cable. And then there is this option which says automatically choose connection type. Depending on the devices, it will automatically put the cable, whatever is the appropriate cable, it will use that automatically. So that's again a good feature of Packet Tracer. You need not to worry if it should be if it should be straight through cable or crossover cable. You can directly select automatically choose connection type and it will put the appropriate cable. And yeah, that's a quick introduction about how to use Packet Tracer. Rest, like I said, you can follow this blog. It explains you everything. It tells you even how you can add devices, how you can configure IP, connect the devices, how to make a communication between them. You can definitely have a look on this particular blog and it will teach you much more, right? So you guys have to download this and get an introduction to this. Try it before our next session, which is going to be on Monday now. So that's a task for you all. And yeah, that also brings us to the end of this particular session. So if you have got again any doubts or queries, you can let me know. Otherwise, we'll wrap it up. Okay, thank you so much, everyone. Do attend the session that I have told you about yesterday. It's a webinar about understanding subnetting, so it will be a good revision for you all. And that's going to happen at 6 p.m. Indian Standard Time. So you can register for it and can get yourself the link to attend the session. So thank you so much. I'll see you all at the webinar. Take care. Bye-bye. And do practice whatever we have learned today. Thanks again.